Welcome. Have you ever looked up at the night sky filled with countless sparkling stars and wondered where it all began? Let's embark on this journey together, filled with countless sparkling stars and wondered, where did all of this come from? It is perhaps the biggest, most profound question we humans can ask. Think about it for a moment. Everything you see, everything you touch, even you yourself, it all had to begin somewhere. It wasn't just always here. The story of our universe is the ultimate origin story, a tale of unimaginable energy, mind-boggling scales, incredible transformation. It's a story that connects every single one of us to the farthest reaches of space and the very beginning of time itself. So, are you ready to go on an adventure to the dawn of everything? This journey begins with an idea so powerful it changed how we see everything. Before this idea, many people thought the universe was static and eternal, just sitting there forever. But science, which is our way of asking questions and testing the answers, has shown us something far more exciting and dynamic. The universe had a beginning, and what a beginning it was. Before we dive into how it all started, let's get on the same page about what the universe even is. In the simplest terms, the universe is everything. And when I say everything, I mean everything. It includes all of space, all of time, and all of its contents. That means every star you see twinkling in the sky, and all the ones you can't see. It includes our planet Earth, the Sun, the Moon, and all the other planets in our solar system. It includes the vast, empty-looking voids between the stars and the mysterious, invisible stuff we call dark matter. If it exists in any form, it's part of the universe. It's the biggest container there is, and there's nothing outside of it. Think of it like this. Your room is in your house. Your house is on your street. Your street is in your city. Your city is in your country. Your country is on a continent. The continent is on planet Earth. Earth is part of the solar system. The solar system is a tiny part of the Milky Way galaxy. Visual. Zoom out. Earth, solar system, Milky Way, cosmic web. So, how did this whole cosmic show get started? Scientists call it the Big Bang. Now, the name is a little misleading. It wasn't a bang like a firecracker exploding in an empty room. There was no space for it to explode in, and there was no air to carry a sound. The Big Bang was the beginning of space and time itself. It was an event, an incredibly hot, incredibly dense single point. That point began to expand and cool. It carried all the energy and matter of the universe with it. Imagine a compressed spring suddenly being released. Imagine a balloon inflating from a tiny dot. That's a better way to think about it. A rapid, ongoing expansion. Why do scientists think this happened? We have clues. First big clue: the universe is expanding. In the 1920s, Edwin Hubble observed almost all galaxies moving away from us and from each other. The farther away a galaxy is, the faster it's moving away. Exactly what you'd see if the entire universe were expanding. Imagine baking raisin bread. As the dough rises, every raisin moves away from every other raisin. No single raisin is the center. The whole dough expands. Our universe is like that. Galaxies are the raisins. If it's expanding now, everything was closer in the past. Run the clock backward. Calculations show everything squeezed into one hot, dense point about 13.8 billion years ago. The very first moments of the universe were a whirlwind of unimaginable conditions. Let's zoom in on the first second after the Big Bang. It was a time of such extreme energy and temperature, trillions upon trillions of degrees. that the laws of physics as we know them were just beginning to take shape. In the tiniest fraction of a second, a process called inflation is thought to have occurred. During this mind-bogglingly brief period, the universe expanded faster than the speed of light, growing from the size of an atom to the size of a grapefruit almost instantaneously. This incredible burst of expansion smoothed out the universe, making it incredibly uniform, which is something we still observe today. Right after inflation, the universe was a super hot, bubbling soup of fundamental particles. It was too hot for even the basic building blocks of matter to exist: protons, neutrons. Instead, it was a chaotic mix of even smaller particles: quarks, electrons, photons. Think of it as a cosmic particle accelerator, but one that filled all of space. Particles were constantly being created from energy and then annihilating back into energy. A frantic dance governed by Einstein's famous equation, E equals mc squared. This soup was opaque, meaning light couldn't travel very far without bumping into a charged particle, making the entire universe a foggy, glowing plasma. For the next few minutes, the entire universe was like the core of a giant star. The temperature had dropped to about 1 billion degrees, still incredibly hot, but cool enough for a crucial event to happen: nucleosynthesis. This is just a fancy word for the creation of atomic nuclei, protons, neutrons, which had formed in the first second. Now they began to fuse together. This process cooked up the first, simplest atomic nuclei. Mostly, it created the nucleus of deuterium, an isotope of hydrogen: 1 proton, 1 neutron, and then helium: 2 protons, 2 neutrons. The universe was busy manufacturing the raw materials for future stars. This cosmic cooking show didn't last long. After about 3 minutes, the universe had expanded and cooled so much that fusion stopped. Density and temperature were no longer high enough to force nuclei together. This left the universe with a very specific recipe of ingredients. About 75% remained as simple hydrogen nuclei, single protons. About 25% was converted into helium nuclei. Tiny trace amounts of lithium remained. This prediction, 3/4 hydrogen and 1/4 helium, is one of the Big Bang's most successful predictions. When we look at the oldest stars and galaxies, that's exactly what we find. After the universe became transparent, it entered a period known as the Cosmic Dark Ages. That might sound dramatic, but honestly, it's a pretty accurate description. The universe was just filled with hydrogen-helium gas, but there were no stars yet to light it up. The brilliant light of the Big Bang had faded and stretched into invisible microwaves. For millions of years, the cosmos was this vast, dark, and mostly uniform sea of gas. But it wasn't perfectly uniform. Thanks to that initial burst of inflation, there were tiny, minuscule variations in the density of the gas. Some areas were just a tiny bit denser than others, maybe by just 1 part in 100,000. These tiny irregularities were the seeds of everything to come. This is where our old friend gravity gets back on stage for its starring role. Gravity is a patient force. Over millions of years, it began to pull more and more matter toward those slightly denser regions. The denser a region became, the stronger its gravitational pull, and the more gas it attracted. It was kind of like a slow-motion snowball effect, but on a cosmic scale. Over eons, these small clumps of gas grew into massive clouds. As the first stars lit up the cosmos, they began to group together, drawn by their mutual gravity. These small groups of stars were the first proto-galaxies. Over hundreds of millions of years and even billions of years, these smaller collections of stars merged and collided, growing larger and larger. This is how the grand spiral galaxies like our own Milky Way were built. Gravity wasn't just building galaxies. It was sculpting the entire universe on the largest scales. The tiny density variations from the beginning of time created a vast, invisible scaffolding of something called dark matter. We can't see dark matter, and we don't really know what it is, but it has gravity. In fact, there's about 5 times more dark matter in the universe than the ordinary matter that makes up stars, planets, and us. This dark matter formed a huge interconnected network of filaments and clumps, a bit like a spider's web. The scale of our universe is truly difficult to comprehend. Let's talk about age. As we've learned, the universe is about 13.8 billion years old. That is an incredibly long time. To put it in perspective, if the entire history of the universe were compressed into a single calendar year, the Big Bang would happen on January 1st. The Milky Way galaxy would form in May. Our solar system and Earth wouldn't appear until early September. The first complex life would arise in November. Dinosaurs would roam the Earth for just a few days in late December. And all of recorded human history would flash by in the last 10 seconds before midnight on December 31st. We are incredibly recent arrivals to the cosmic scene. Now let's talk about size. The part of the universe we can see, the observable universe, is about 93 billion light-years in diameter. A light-year is the distance light travels in 1 year, which is about 9.5 trillion kilometers, or about 6 trillion miles. So we're talking about a distance that is almost impossible to imagine. And that's just the part we can see. The true size of the entire universe could be much, much larger. It might even be infinite. We just don't know. We live on a tiny planet, orbiting a typical star in one of hundreds of billions of galaxies. It's a humbling perspective. As much as we have learned about our universe, our knowledge is just a small island in a vast ocean of mystery. For every question we answer, we uncover a dozen new ones. This is what makes science so exciting. It's not about having all the answers. It's about the thrill of the chase, the joy of discovery, the endless pursuit of understanding. Our journey to comprehend the cosmos is far from over. In many ways, it has only just begun. The universe is the ultimate puzzle, and we are the detectives, trying to piece it all together, one clue at a time. Some of the biggest unanswered questions are about the very things that dominate our universe. What is dark matter? We can see its gravitational effects, but we have never detected a particle of it. And what about dark energy? What is this mysterious force that is pushing the universe apart at an ever-increasing rate? And what about the very beginning? The Big Bang Theory describes what happened from the first fraction of a second onward, but it doesn't tell us what caused the Big Bang or what, if anything, came before it. This is why we continue to explore. We build bigger telescopes, like the James Webb Space Telescope, to peer deeper into space and further back in time. Exploring the universe is an expression of our deepest human curiosity. The adventure is just getting started.